once Rutherford's nuclear model of the atom was confirmed, the research started going on about trying to determine how the electrons were arranged outside of the nucleus. The most prominent model that followed Bohr or Rutherford's model is the Bohr model. What Bohr did was he looked at how atoms responded, or samples of atoms responded to energy being added to them. The evidence that he looked at was that when he added this energy to a sample of an element in the gaseous state, a pattern of light was emitted that was a characteristic property of that particular element, similar to a fingerprint. What's more, the light that was emitted from the element was of particular wavelengths, which corresponded to particular frequencies and very specific energies. In order to understand what this means, we're going to take a quick look at light and the theory behind how light operates. So first of all, light has a particle nature to it as well as a wave nature to it. The wave part of it, the properties that are going to be significant to us, are the wavelength, which would be the distance from one peak to the next peak, which would also correspond to the distance from one trough to the next trough, so that would be the wavelength. They list the wave amplitude up here, the distance from the midpoint to a peak or the midpoint to a trough. We won't really be using that too much. There's the frequency of the wave. So the frequency of the wave, if you stand at the beach and you look down at a rock in the sand and you count the number of waves that go by in a minute, the number of waves that go by in a minute would be a frequency. So it's the amount of time something happens it's the number of times something happens over time. So oftentimes these are the number of waves per second, which is given the unity of hertz. The other kind of significant thing here is the relationship between frequency and wavelength. If we take the wavelength, just given the symbol lambda, and we multiply that times the frequency, what we have is the wave velocity. And it just so happens that these light waves that are given off are all traveling at the same speed, which is c, the speed of light, which is equal to 3.00 times 10 to the 8th meters per second. So it's going to be one kind of important thing for us to remember, that formula, that c is equal to the speed of light is equal to the wavelength times the frequency. The other one, you recall, I mentioned that the energy factors in here as well. Turns out that energy is proportional to the frequency. And to make this into an equation that we could solve, we have energy is equal to Planck's constant, h, times the frequency. We'll do a couple of calculations with this in class, or both of these, but these are the mathematical relationships that describe energy, frequency, and wavelength for waves. So let's go back and take a look at our light waves. All right, so if we take a look up here at the waves, you see in the bar here our kind of spectrum of different colors or wavelengths in the visible region. If I go down at the low wavelength end, say at 400 nanometers, 1 nanometer being 10 to the negative 9th meters, we see that there's a corresponding frequency over on the left, and there's a corresponding energy of the photon over on the right. If we go to a larger wavelength, so say we go up to around 500 nanometers, you'll notice that as we go from a larger wavelength, we end up with a lower frequency and a lower energy. And we can go up to 600 nanometers, and again, the frequency gets lower yet, energy gets lower. So as that wavelength gets longer, the energy and the frequency both go down. Right? So up around in that red region, red is actually a very low energy photon in the visible region. Now, if we take a look at where the visible region falls in the larger spectrum of what we call the electromagnetic radiation, the visible region you can see is just a very narrow part of this. If we go higher in energy than the blue, we have ultraviolet, and then X-rays and gamma rays. If we go lower than the red, lower energy than the red, we get to infrared, microwaves, radio waves, and FM and AM carrier waves. So you can see that visible light is, in terms of the nature of it, is exactly the same as ultraviolet, X-rays, gamma rays, which are very high energy. We know they can be potentially dangerous to us, as well as microwaves and radio waves and infrared rays. The difference is, again, the energy. Now, down at the bottom, we see the spectrum for hydrogen. So again, what we have is, for the element hydrogen, if you excite a sample of hydrogen in the gaseous state, you're going to get wavelengths that are given off of these particular values here, and you can see them in the box there. Again, what's significant here is that no other element will give off that same spectrum. So that's the first thing. And the second thing is that you get certain wavelengths which correspond to certain energies, which tells us something very important about the arrangement of the electrons in the atom, that when the electrons gain energy, there's only certain allowable energies that they can have, and we'll see what that is in just a moment in an animation, but they can't just get random amounts of energy. They have to possess very specific amounts of energy. All right, so here we have something that will help us see it a little bit better. So if we add energy to an atom, that atom's going to go up to an excited state. Right? So here's an excited lithium atom. That's a very unstable state. So what will happen is that the atom will drop down to a lower state, perhaps the lowest state, which would be called the ground. The ground state would be the lowest energy state. In the process, when it drops down, it's going to release a little bundle of energy, a photon, in this case of red light. And that energy corresponds to the drop in energy from the excited state down to the ground state. If that separation between the excited state and the ground state were larger, then you would get a larger energy gap, and you would get something with a shorter wavelength, perhaps than red. This animation may give us a little bit of an idea of what's going on here. So I've got a light source over here on the left, on the top, hydrogen atom here in the middle, and over on the right is a photon detector. So that photon detector is going to register the wavelength of the light that is being emitted from the atom. The light source is going to add a photon to the atom, so that's the energy being added. So let's go ahead and do that. Down in the lower left, we can change the wavelength that's of light that's being shown on the hydrogen atom. So I'll go ahead and send the photon in there. And you can see that the atom alters slightly, and then it releases a photon. And the photon that was released had the same wavelength as what we sent in. It doesn't always have to be the case there, but in this case it does. We'll do that again, and this time take a look at the box on the bottom right. The little arrow in that box in the n equals 1 level represents the electron in the hydrogen atom. So watch that electron, see how it jumps up to the second level. When it falls down again, that photon is released. All right, let's go up to a shorter wavelength. So this would be a higher energy. So that electron in the n equals 1 level now has a potential to bump up even higher. So again, we send a photon in, we get another change in the hydrogen atom, jump all the way up to the third level. Notice that drop down to the second, gave off a photon. From the second to the first, gave off another photon. Let's see that one more time. So the high energy photon causes the electron to jump up to n equals 3, falls to n equals 2, releases some energy, and then from the second level drops to the first level and again releases more energy one more time. Up to the third level. This time the photon that was released was a result of the electron dropping from the third level all the way back down to the first level. And finally, let's try the shorter wavelength, which again would be the highest energy of these three. Electron jumps all the way up to the fourth level. This, in this case, falls all the way down to the first level, so just releases the one photon. Again, jumps all the way up to the fourth level, falls to the second level, releases some energy, then falls to the first level and releases the another amount of energy. So if we think about it this way, if we start with an electron in its ground state, so the lowest energy level, so this would be for a hydrogen. If we add energy to that, so say we make it jump up to the fourth level, right? Well, that electron in the fourth level then, in the excited state, could drop down to the third level and it will release a photon of light of a particular wavelength. It could drop down to the second level and again would release a slightly different amount of energy, or it could drop down to the first level. And obviously the longer the drop, the higher the amount of energy that you would have, but the shorter the wavelength. So you get different colors based on which transition the electron was going from. And so some of those in the videos you saw where it could drop from the fourth to the third, and then perhaps from the third to the first, or the third to the second. And so you can see how we would get very specific energies of light given off. The idea of the electron being able to exist at certain levels and not an energy in between these, so if we think of this as energy levels, the idea of this is called quantized energy levels. Oops, excuse me. And this is probably the most important thing to come out of Bohr's model of the atom. Next, we'll have to kind of work from, this is just a starting of what's going on with the electrons. The next development was going to be called the quantum, the wave mechanical model of the atom, or the quantum mechanical model of the atom.